Okay, so we're working this one. We have a right circular cylinder that's inscribed in a sphere of radius r. Now, I did an example in class where the radius was 9, I think 9 feet or something like that. Here, we're not given the radius of the sphere, so we're just going to leave the sphere is going to have some arbitrary radius, which I will call lowercase r to match what's here. All right, that's fixed. Okay, this is a constant. It's given to us. We don't know what it is though. All right. So now we have a cone, a right circular cone that's inscribed. So we have this cone, comes down, touches here, comes over, touches over there, touches at the North Pole. And we're trying to figure out the largest possible volume of such, oh wait, hold on, this is cylinder. Oops. That's probably why people have problems. Okay, cylinder is in here like this. So it looks like this, not a cone. With me?
Yes.
Okay, so we want to find the largest possible volume of that cylinder. Now, this cylinder has its own radius, which is not little r. Okay, because the radius of little r is the distance from the center of the sphere to the outer edge of the sphere. And this cylinder could be, you know, it could be really, really narrow and tall, right? Or it could be really, really wide and not tall. Right, so we have these different, depending on how we draw the cylinder, it could have a different radius. So it's definitely fluctuating, that radius on the blue. So I'm going to call that capital R to distinguish it from little r. Call this capital R. And then this cylinder also has some height that I don't really know right now. I'll just call it H. And so if we look up the volume, because we're trying to find the largest possible volume, the objective here is to find the volume of the cylinder as big as we can get it inside that sphere. So the volume will be, you just got to look it up. It's pi times the radius, which is capital R squared, times the height. That's the formula for the volume of the right cylinder. That's the objective. We want to make that as big as we can. We have two variables in there, R and H. We need it to be a single variable. So now we talk about the constraint. And to figure out the constraint, we're going to need to do some stuff we did in the past, which was like cut this in half and take a look at a cross section. So if we cut it in half, terrible. If we cut this in half and look at it from the side, we're going to have some arbitrary rectangle in here like this. What we're going to try and do is establish some relationship between capital R and little h. And so I can identify the center of the circle would be the same as the center of the sphere. And then this distance from here to here, that is h. I know that the distance from here to the rectangle right there, I know that distance right there is capital R. And I can see that if I connect this outer point to the center, I know that's little r, which is a constant. So I created a little triangle in here. This little triangle looks like this. Capital R, little r, and then this is half of h. Because h goes from the top all the way to the bottom. If I just go from the center up, it's half of h. And now with this, I can set up a relationship between capital R and little h using Pythagorean. So I know capital R squared plus 1/2 little h squared must be equal to little r squared. And what I'm going to do is I'm going to solve this. I'm going to solve it for capital R squared because that's what I have in my formula here. So I can just simply move the 1/2 h squared to the other side, subtracting it. And let me go ahead and square that. Capital R squared equals little r squared minus 1/4 h squared. So I squared both the half and the h to get this. This is the formula for capital R squared, and it's in terms of h. So I can come back up to my formula, take this, come back up to this, and now substitute. I should probably write that constraint down over here. My constraint is that I must follow this equation. Okay, that's my constraint. And now I replace the r squared in here. So I get v equals pi. R squared is little r squared minus 1/4 h squared. And then all of that times h. Then I'm going to do one more thing. I'm going to distribute the h through the parentheses and the pi through. So my volume will be pi little r squared h minus, and then over here, 1/4 pi, and then h cubed. So the h went to here, got h cubed, the pi came in and hit the 1/4, I've got minus, this is it. This is my volume function, and I'm actually can look at it as a function of just h. This is it, this is the objective function. Now, don't let this r throw you off. That is a constant. Just imagine that's a number that's been given to you. Okay, so this truly is a function of one variable. The only variable in here now is h, which means I can differentiate and do all the things that I want to do.
Is there some kind of, I don't know, giveaway that r is a constant instead of seeing it like it's a variable?
Yeah, because it says a right circular cylinder is inscribed in a sphere of radius r. So that's it. They are fixing r right here. They're not telling you what it is. They're just telling you that it's some radius. So our answer is going to have little r in it. There's no way I can give you a numerical answer because I don't know what r is. So our answer, little r, I don't know what it is. So let me just keep going, and then you'll see in the answer that it'll be a general answer in terms of little r. And then if we wanted to replace r with a number, we could. So this is like getting a general answer for any sphere with a cylinder inside of it. So is there a restriction on h? I'm trying to figure out if I want to do the open interval or closed interval now. So is there a restriction on h at all here? So think about h in your picture.
I mean, I don't think it has a numerical restriction. It can't be bigger than the actual like the diameter of the sphere, but it's,
yeah, exactly. Which would be what?
2 pi r.
Just 2r, right? Because think of it this way. Look at it in this picture. The height here, if the height went all the way to the top and then all the way straight down, right? Then that would be twice the radius. Agreed? Twice the radius
Yes.
is the diameter. That's the biggest h could ever be. So h has to be at least smaller than or equal to 2r. And it must also be bigger than or equal to 0, because if h is 0, you're basically, you don't have any height to the cylinder. So it's basically like a flat sheet. Does that make sense?
Yeah.
If h is 0. So one extreme is if h is 0, it's a flat sheet, which wouldn't have any volume to begin with. And then the other extreme is that h is 2r, which means you would just have a single line going down the center. And that wouldn't have any volume either. But those are the extremes. So now I'm ready for a derivative. I'm going to use the closed interval method. The derivative of this is, and again, remember, r is a constant, little r. So this is just pi r squared, because I'm really just taking derivative of h, which is 1. And then the pi r squared comes for the ride. And then I have to take derivative of h cubed, so the 3 comes out. So that gives me minus 3/4 pi, and then h to the second power. And so I want to know, when is this derivative equal to 0? And then I want to know, when does the derivative not exist? Well, the derivative not existing is not going to happen, because this is just a polynomial. It has h squared in it. There's no other division by 0 or division by anything or square root. So I'm not even going to look at that. If I set this equal to 0, I can just start moving things around. So I move this negative term to the right side. I can divide both sides by pi. And then I can multiply both sides by 4/3 to get the reciprocal, so it cancels out on the right. and then I take the square root. So when I take the square root on the right, I get h. On the left, I would get a plus or minus, but I'm going to throw away the minus because h is the height and it has to be positive. So I'm only going to take the positive of this. And I'm taking the square root of all of these. So 2 over root 3 r. And so that's my only critical value. And so I need to take my original function up here. I need to take this. And I need to evaluate that because I'm using the closed interval method. I need to evaluate that at the endpoints, 8 at 0 and at 2r. And then I also have to evaluate it at this critical number that I found, 2 root 3r, and figure out what the volume is. So if you plug 0 into this for h, everything goes away, you get 0. So you have no volume. If you plug 2r in for h, watch what happens. You get pi r squared times 2r minus 1/4 pi, and then I'm going to take 2r and I'm going to cube it. So I get pi r, let's do it this way. 2 pi, that's just the 2 times the pi, and then the r squared times r is r cubed. And then over here, if you cube the 2r, you get 8r cubed. So minus 1/4 pi 8r cubed. The 8 and the 4 reduce. So you wind up getting 2 pi r cubed minus, again, 2 pi r cubed, which is 0. So you have no volume here, no volume here. And if you plug this in, then you are going to get some volume. You're going to get, let me see, pi r squared. Now I replace h with 2 over root 3r, then minus 1/4 pi, and then 2 over root 3r cubed. And this is some number, it's not going to be 0. So this is kind of messy, but 2 root 3 pi r cubed, that's just multiplying 2 over root 3 times the pi in front, then r squared times r cubed. Over here, I cube the top and I cube the bottom, or I cube everything in here. So I get minus 1/4 pi. Cube the top, you get 8. If I take root 3 and cube it, root 3 times root 3 times root 3, 2 of them come together and give me a 3. So I get a 3 root 3. And then I have an r cubed here. The 8 reduces with the 4. I get 2 root 3 pi r cubed minus, let's see, this canceled. I should have a 2 over 3 root 3 r cubed. Nothing cancels. I can get a common denominator between these two, so I need to multiply 3 here and 3 here. That gives me 6 over 3 root 3 pi r cubed minus 2 over 3 root 3 r cubed. And now these are like terms. We can just subtract. Just take this and this, those two together, subtract them. So you should get 4 over 3 root 3, then the pi, then the r cubed. That is the most volume you're going to get. And do they want the dimensions? No, they want the largest possible volume. There it is. What do you think?
Damn.
Yeah. Your answer has R in it though. See? So now
I do that.
What's that?
I say, yeah, I do understand that. Like say it's a constant, you're just leaving it there.
Yeah. So now if you told me, hey, that sphere has a radius of 1, then I tell you, oh, then the biggest volume you're going to get is put a 1 in here. Okay, and that would be at 4 pi over 3 root 3. That would be the biggest volume. Let me just check the answer. I hadn't really done this one. 4 pi r cubed over 3 root 3. Yeah, that's right. 4 pi r cubed. Yeah. All right. I'm going to stop that recording. We've got to get to class.